In this work, we propose a new framework to model the exterior of residential buildings. The main goal of our work is to design a model that can be learned from data that is observable from the outside of a building. To represent a three-dimensional building, we propose a parametric model to describe the mass model, roof and facade elements of a building. Unfortunately, it is very difficult to learn a model where each building is described by a varying number of parameters. Therefore, we additionally propose an intermediate attribute-based representation with fixed dimensionality. Second, we propose a hierarchical graphical model with hidden variables to encode the relationships between building attributes. Third, we provide optimization algorithms to generate three-dimensional models based on building attributes sampled from the graphical model. We present a building as a union of a set of boxes and the placement of facade elements and roof information. The problem of this representation is that each building has a different number of parameters. Our attribute-based building representation overcomes this problem. Each building is described by a fixed set of attributes classified into three categories. Firstly, 7 attributes are defined to describe the mass model of a building. The attributes can be multidimensional, so we show each dimension as a coloured box. 3 attributes describe the facades of a building. Further, 3 attributes describe the element styles of a building, including the roof and window style. We generated a building database of 200 buildings consisting of building footprints and photographs. For each building, the user first marks the garages and the porches in the 2D building footprint. Next, observed facade elements can be marked on each available facade images. Finally, all the attributes are computed automatically. We design a probabilistic graphical model with a hierarchy of hidden variables to represent the joint probability distribution of building attributes. At the root of the model, S can be interpreted as the overall style of a building. For each mass model and facade attribute, corresponding hidden variables represent the styles of each attribute. Finally, observed random variables describe attributes extracted from the data. There is a one-to-one correspondence between observed variables in the graphical model and attributes in the attribute-based building representation. For example, each of the 7 mass model attributes corresponds to a node MCI. To encode the conditional dependencies between the observed random variables, the model also includes lateral edges between variables in each category. Here we visualize lateral edges between nodes describing mass model attributes. We did not detect meaningful edges between facade attributes. In the element attributes category, we learned one edge between roof style and window style. After training, the graphical model describes the joint distribution of building attributes factored as a product of conditional probability distributions. Finally, we can sample the building attributes from the trained probabilistic graphical model. Given a vector of building attributes, we would like to compute the corresponding parametric building representation. First, we minimize the proposed mass model energy to generate the mass model. We employ simulated annealing to generate the mass model according to the mass model attributes. Here is the result. Then, we add roofs using a straight skeleton algorithm and the roof style attributes. The next step is to place elements on the facade of the model using a genetic algorithm and quadratic programming. There are 2 major applications to our work. One application is building synthesis. Given our database of 200 buildings, our model can learn 7 different building styles. Here are 2 synthesized buildings of each style. Here are additional synthesized buildings. The other application is building completion. Starting from a single image, a user can mark observed parts and then automatically compute a complete 3D building model. First, the user can specify the scale of the image, in this case using the garage. Next, the user specifies the observed faces of the mass model. Next, the user can mark shapes on the observed faces. Here we visualise the marked parts of the building. Using this information as input, we now sample building attributes and automatically complete the building. Here we visualise the completed mass model. Here are the completed roofs of the building. Now we add the facade elements abstracted as boxes to the visualisation. Finally, the complete 3D building uses assets for its detailed geometry.